Thank you very much. Thank you for coming. Good evening. Can everyone hear me? Okay. If it's difficult to hear me, I can grab that microphone. Is it fine now? Perhaps. Okay, I'll just grab the microphone. It's okay. Better? Oh. No. Better? Like this? Yeah. Okay. Thank you for coming. My name is Sander Dalm. I work for the Netherlands Forensic Institute. And today I'll tell you about a method that we are developing for evaluating forensic evidence using machine learning. And to do so within the Bayesian framework, which is the framework of likelihood ratios, which is a very common framework. It's actually almost the framework in the world of forensic science. I'll give you a really short bio about myself. 2009, I graduated in biological and cognitive psychology at the Erasmus University Rotterdam. So I actually have a background in the social sciences. Within the world of social science, the statistics topic has always been my favorite topic. So I've worked mostly as a statistical researcher. I've worked for Statistics Netherlands, or CBS. I've worked for the Ministry of Justice and Security, Ministry of Science, Culture and Education. And now I work for the Netherlands Forensic Institute as a data scientist. My job includes evaluating forensic evidence, which is the topic of today's presentation, but also clustering, searching data, creating visualizations, helping people get insight from data, and also deploying deep learning algorithms, because we all love deep learning algorithms. The team at the Netherlands Forensic Institute where I work is called Forensic Big Data Analysis, which is as cool as it sounds. We are a team of 16 data scientists, and our most important job is to find forensically relevant patterns in large amounts of data. Examples are using deep learning to recognize weapons and drugs in images, large amounts of images, millions of images, detecting suspicious patterns in financial data, doing author recognition, clustering, searching large amounts of text. The police can actually do data analysis themselves, but when the amount of data is too large, or when special expertise in terms of clever algorithms is needed, people often come to us to help them out. And sometimes we also evaluate evidence based on the likelihood ratio framework, which is what I'll talk about today. Our data sources are very diverse, which makes it really fun and challenging to work at the Netherlands Forensic Institute as a data scientist. They may come from confiscated phones, confiscated hard drives, license plate cameras, but also from telephone providers and many different sources. So today I'll talk to you about a fictional crime case. And in this crime case, we would like to know who was the user of a particular prepaid cell phone. And we want to do that by matching movement patterns from cell phone data from two cell phones to see how closely they match and how likely it is, or actually how likely the evidence is under the hypothesis that the phones have the same user and under the hypothesis that the phones have different users. So let's say that an ATM machine is blown up, a lot of money is stolen, a prepaid phone is lost in the chaos, it's found by the police. There's also a suspect. There's not a lot of evidence against the suspect, but maybe if we can link the suspect to the prepaid phone that was found on the crime scene, we may be able to convict him. So the research question is the suspect the user of the prepaid phone? Exactly what information do we have? Well, we know the phone number of the suspect's private phone because everyone has a private phone. We also know the phone number of the prepaid phone that was found. And the telephone provider can provide us with usage information from both those phones. So whenever a phone call is made or received, or a text message is sent or received, we know when that happened, and we also know to which cell tower the phone connected. Your phone always needs to connect to a cell tower. It has a limited range. It typically wants to connect to a very close cell tower. So if you know the ID of the cell tower to which your phone connected, it's possible to know with some accuracy where you're hanging out, basically. So it may seem like an easy problem to determine whether two phones have the same user or different user, because you would expect phones by the same user to always be close together, and phones by different users to always be far apart or to only sometimes be close together. But in reality, it's quite a difficult problem. And the problem is that a cell phone doesn't always connect to the closest cell tower. There are various things that may influence the cell tower to which your phone connects. Obstacles like tall buildings or trees, weather conditions, the number of people currently using the network, the direction of transmission. Cell towers don't actually send their signal in a circle, but they send it in a particular direction. So you may be very close to a cell tower, but it may be sending in the wrong direction, so you connect to a different cell tower. And also in theory, most cell phones have a range of 35 kilometers. So the data are really, really imprecise. So that makes it difficult to determine locations with accuracy. Another problem is that the data are sparse. We only have data when people actually use their cell phone. Most people don't use their phone all day. Some people do, perhaps. So if you look at the figure on the left, let's say that each color represents a cell phone. And on the x-axis we have time. On the y-axis, let me try out my laser beam. On the y-axis we have location. In the figure on the left, it's really obvious that the green phone and the black phone belong together, while the blue phone seems to deviate in its movement patterns. It's very clear that these phones have different users and these phones have the same user. But that would be an ideal case. In reality, the data look more like this on the right. The data are sparse. People are not sending text messages all day. They're not calling all day. So we have a very sparse picture. And it's a lot more difficult to see which phones belong together and which do not, especially when you have hundreds or thousands of phones. So we need a machine learning method. So here's an example. So these are GPS data. They are about the best location data that you can get. This is a trip from Den Haag to Apeldoorn. I think it's taken by train. So this is not what our data look like. The data that we have are just the locations of these little black symbols which represent the cell towers. So what we really have is something like this. We see that phone number 1 connects to a cell tower at 11:47 on this location, and then phone number 2 connects to this cell tower at 13:16, and so on and so on. You can kind of see that they're going in the same direction, but it's really difficult. So to summarize, we want to know if a suspect is the user of a certain prepaid phone that can be linked to a crime. By the way, the reason suspects may be using a prepaid phone is because most criminals are smart enough not to use their own private phone when arranging their criminal activities. It will be too easy to trace the communication, so they try to be smart. They buy a separate phone, which they immediately throw away after the crime has been committed. Or if they're smart, they burn it or do something to it. So a lot of criminals walk around carrying 2 phones. We know when and where the prepaid phone was used. We know when and where the suspect's phone was used. But the data are very sparse and they are also imprecise. So that's our problem. First, I'll talk about an intuitive approach that you may think of to solve this problem, but that doesn't actually work very well. And the reason I'd like to discuss it is because understanding why it doesn't work, I think, is really informative, and it highlights some of the problems and difficulties of forensic science. So one thing you might suggest is to collect a large database of movement patterns from many different phones, perhaps thousands or millions of phones, and to sample from that database pairs of cell phones, and to calculate something like the average distance between the phones. And your assumption may be that phones that have the same user tend to be closer together, and phones that have different users tend to be further apart. So perhaps if we take the phones in question, the suspect's phone and the prepaid phone, it will be an enormous outlier in this distribution. I'm not sure if you would actually get a normal distribution, you would get something. And the phones in question may represent an outlier in this distribution. So let's say that the suspect's phone and the prepaid phone are very close together on average, and they are all the way in the tail of the distribution, and the probability of being this close together is only 0.1%. So what can we do with that information? I'm going to argue that you can do almost nothing with that information. There are some problems with outlier detection. One problem is that improbable events happen every day. The probability that someone with exactly your DNA is born is almost zero, yet we are all here. So the fact that improbable things happen doesn't really mean very much. Also, there's always someone in the tail of the distribution. So even if you have a land of perfectly honest people who never commit any crimes, as soon as you start making distributions, you will get outliers in the tails of those distributions. It doesn't necessarily mean anything. The most important problem is that in forensic science, you're never just thinking about one hypothesis, you're always thinking about two competing hypotheses, and they're often called HP, which means the hypothesis of the prosecutor, and HD, which is the hypothesis of the defense. So for example, two DNA samples, they either come from the same person, hypothesis one, prosecutor's hypothesis, or they come from different people, which would be the defense hypothesis. A fingerprint, it may be a match, prosecutor's hypothesis, or it may not be a match, defense hypothesis. Two phones may have the same user, or they may have a different user. So I'll illustrate the problems of outlier detection with an example. So let's say that we just have this distribution. Let's call it the blue hypothesis. And we also have one observation, which is the black arrow. And as you can see, our observation is very unlikely under the blue hypothesis because it's all the way, well, almost all the way in the tail of the distribution. So does this mean that we should reject the blue hypothesis? Well, that depends. If you're going to assume that there is an alternative competing hypothesis that is much more likely, or actually where the data is will be much more likely, this will be evidence against the blue hypothesis, and for, in this case, the black hypothesis. But your assumption may just be wrong. Perhaps the alternative distribution looks like this. So the very same observation may either be evidence for the blue hypothesis or against it. So what we need is not just an estimate of one probability distribution. What we need is a likelihood ratio. And a likelihood ratio is the ratio of the probability of a piece of evidence given two competing hypotheses. So in this picture, it's the term in the middle. You have an observation, and you'd like to know how likely is this observation under the prosecutor's hypothesis, and how likely is it under the defense hypothesis. Knowing the likelihood ratio gives you information about the posterior odds, about the probability of the hypothesis, but it doesn't give you all the information. There may be many likelihood ratios if you have many pieces of evidence. And you also need to take into account the prior odds. And not taking these things into account is actually the source of a lot of common fallacies, which I will talk about later in this presentation. But the basic intuition is that you try to estimate the distributions of two hypotheses and then evaluate the evidence against them. So this is our approach to the problem. It's a machine learning approach. We first collect a lot of data from cell phones, movement data from cell phones. Some of these cell phones have the same user, and some of these cell phones have different users. And I'll tell you a little bit more about the data collection process later. And we then train a machine learning system that tries to classify, based on a few features that I'll talk about later, whether or not two phones have the same user. So the prosecutor's hypothesis and the defense hypothesis are almost directly classified by the machine learning algorithm, except that we first apply the machine learning algorithm to a bunch of validation data, which are not used to train the model, to estimate what these distributions actually look like. So once we have a machine learning model, we can take the phones in question, the suspect phone and the prepaid phone, score those phones, score those data according to that same machine learning model, and look up that score in this graph to calculate a likelihood ratio. Is the score more likely under the prosecutor's or under the defense hypothesis? So this would be the likelihood ratio that results from that. We first need to collect a lot of data, so I actually brought a little prop with me. Data scientists at NFV, we sometimes carry these little bags around. They contain a few cell phones, 3 of them, one for each provider, a KPN one, a Vodafone one, and a T-Mobile one, as well as a battery pack, because cell phones tend to run out of power all the time. We carry these around for, let's say, 4 weeks to collect some data, which means that if I carry one of these bags around and my coworker carries one around, then these phones would be examples of same user phones, and my phones paired with the phones of my coworker will be examples of different user phones. So we are setting ourselves up to estimate both those distributions. We use an app called Network Monitor Log, or Network Monitor, which logs the same information about your phone as your provider does. So every 10 seconds it connects to a cell tower and it records the ID of the cell tower. It also records your GPS location, which is nice because then we can use the GPS data to estimate the accuracy of our cell tower data, because our cell tower data are very imprecise and we would like to know exactly how imprecise they are. So this would generate a usage pattern that is very unnatural. It would basically connect every 10 seconds. Normal people don't do that. So to make these data resemble normal usage a little bit more, we downsample them using a Poisson distribution. There's actually a lot of scientific literature on the calling behavior or cell phone usage behavior of people, and the use of cell phones can be modeled by a Poisson distribution, and usually several Poisson distributions, one per hour. During certain hours you're more likely to make a phone call than during other hours, but within each hour you can model it as a Poisson process. This is what the data will look like. It's actually very simple. You just have a phone ID. It may be phone A or phone B in this example. You have a timestamp and you have a location, a latitude, longitude location. In reality, you would find, for example, that phone A is used 5 times in a row and then phone B is used 3 times in a row. But those observations aren't as useful. What we're really interested in are the transitions from one phone to the next. Because if you have 3 observations of phone A, it doesn't give you any information about our hypothesis, because they would all be, by definition, same user observations. The only way to get a different user observation is, for example, to get a really large distance going from phone A to phone B in a really short amount of time. So we calculate a bunch of features. We calculate the time delta between this record in the database and this record. We calculate the distance between the phones. And we also calculate the speed that a person would have needed to travel in order to explain both observations. So if I use my cell phone now and I use it again 10 minutes later in the same building, then the speed would be almost 0. It would be very low. It would also be very easy to explain those data using just the hypothesis of a single user. If we have 2 cell phones, one is used now here in Utrecht, another one is used 10 minutes later in Rotterdam, the speed that you would have needed to travel in order to explain both those observations will be really high, and it will be really a strong indication of a different user phone pair. The machine learning part, we actually prefer to use a fairly simple machine learning model, a logistic regression for each observation, for each transition. Logistic regression is a simple linear model that outputs a binary label as a function of a linear combination of its inputs. So the outputs are always between 0 and 1. One advantage of logistic regression is that it's an explainable model. It's nice to inspect the coefficients of your regression analysis to see what you're actually calculating. And also because it's a simple model, it has a little bit less of a risk of overfitting the data like more complicated models have, like random forest or neural networks. So we use a fairly simple logistic regression for each observation. But the model is actually applied twice. If we have a phone pair, we first predict on a database of individual rows that are all labeled. They are labeled either same user or different user, because they come from a same user or different user phone pair. But then we're not really interested in individual observations. We're interested in the entire pattern, the entire movement pattern of 2 phones. So what we do is we aggregate these scores into bins. We take all the logistic regression outputs between 0 and 0.1, put them in one bin, between 0.1 and 0.2, put them in the next bin. So we aggregate these data into 10 bins, and then we train another logistic regression model that takes those 10 bin features as input and outputs a probability or a score for the entire phone pair, which is how we aggregate our data. So this model, in principle, should be able to determine with some accuracy whether two phones have the same user or a different user. So now that we have this model, we can unleash it on a bunch of validation data to estimate these distributions. These are some very nice fictional data. In fact, all the data that I'll show you tonight are fictional. So this is not what it would look like in reality. In reality, it may look something more like this. The data may be highly irregular, and these perfectly nice normal distributions, you usually don't find them. Now, if you remember how we calculated the likelihood ratio, this should be a big problem, obviously, because our assumption was that our machine learning model outputs a score, and that higher scores indicate a higher probability of being same user. But to calculate the likelihood ratio, you would divide this by this. Let's say that the score is 0.5. You would divide this frequency by this frequency, and you would get a certain likelihood ratio. But if your score is lower, you see that the likelihood ratio actually increases a little bit, which is weird. It moves in the opposite direction of what you would expect. Also, if you score 0.6, there may be no different user observation here at all. So the likelihood ratio is actually undefined, because you would need to divide by 0. And as we all know, only Chuck Norris can divide by 0. So we need to apply a smoothing operation. One option is kernel density estimation. In kernel density estimation, you replace all your observations by very small Gaussian kernels that have the mean of the observation, but they also have a little bit of a variance. And these Gaussian kernels you can then add together to get a very nice smooth distribution. The variance of your Gaussian kernel is a free parameter, and free parameters are always dangerous because you need to make a decision. And whenever you make a decision, you need to explain your decision, so that's difficult. One rule of thumb you could use is that you would like your likelihood ratio to be monotonically increasing when the output of the classifier increases. So you would need to apply exactly the amount of smoothing that is required to make sure that the likelihood ratio moves in the expected direction. That's one option. There are also rules of thumb that you can find in the literature about how to choose this kernel size. But this is one that we sometimes use. Then you can finally calculate your likelihood ratio by having an observation and looking at the relative probabilities under the different hypotheses. The further you go to the right, the higher the likelihood ratio. If you go really far to the right, it just skyrockets a little bit. It reaches something like 3,000. What we're also interested in is 1 divided by the likelihood ratio, because a likelihood ratio can also give very strong evidence in favor of the suspect. So a likelihood ratio of 0.0001 would be a strong indication of different user, and it's as informative as a likelihood ratio of 10,000 or 100,000. So it's also useful to look at 1 over the likelihood ratio in plots like these. So this summarizes the method. I have a lot more slides about some more philosophical questions and some details, but perhaps if there's already a question about this method, I would like to hear about it. Any questions? Yes?
I'm not a statistician myself, but I think is that the method is based on the naivety of the user. Because what happens when you have a user that disconnects the phone, or other people use the same phone? I think it complicates.
Yes. Yes, you always need to make a bunch of assumptions when you're writing a forensic report. And it's always good to make those assumptions explicit. So when you would do an investigation like this, you would very clearly write in the introduction that we are using this method. We are assuming that the phones aren't shared between people. We may make a bunch of other assumptions. We may assume that people don't know about this method, that they're not consciously trying to send it in the wrong direction. So there's always a bunch of assumptions that you need to make whenever you do forensics. And as long as you make those assumptions explicit, the judge can then decide whether or not those assumptions are actually valid. Any more questions? Oh, yes?
Okay. It's in line with the first question. Actually, you have totally artificial data.
Yes.
How can the telephone company providers cannot provide you with real data of people they know who have two cell phones and actual use and things like that?
Yes.
Because I think that artificial data are always a weak point. It's good for testing your algorithm. It's not, in my opinion, as convincing as it should be.
Yes. Well, we actually agree. This is now a research project that we're doing, and these artificial data are collected for research purposes. In a real case, there may be various other data sources. The police may acquire real data from telephone providers, perhaps not just from the suspect himself or herself, but maybe from many other people who are also suspects. Yes. Well, ordinary people, you know, that privacy might be an issue. Other things that we could do is find people for natural experiments. So there are a lot of people who just naturally carry two phones around, and we may approach them, ask for permission to acquire their data from the telephone provider. So I totally agree with that. It's really important that your data are as representative as possible. Yes.
So as far as I know, on Android you can capture not the nearest tower, but a bunch of towers nearby. So you can resample nearest tower basically. So do you do such resampling, or you only capture the actual tower that the phone is connected to?
Do you mean the app that we use to collect data?
Yes. I don't know the app. I know the API. I assume the app is using.
Ah, yes. I'm actually not entirely sure what the internal workings of that app are. My understanding is that it collects roughly the same information as telephone providers. So if, for example, weather conditions or obstacles, line of sight blockers are interfering with the connection, I'm assuming that will also influence the behavior of that app. Yes.
I thought you said that you were tweaking the kernel to make it a nice, smooth likelihood ratio curve.
Well, not really tweaking.
Can you tweak it the other way as well? So the defense can tweak it in a way that it's not a nice curve that would put there.
Yes, well, I wouldn't really call it tweaking. Tweaking implies that you're trying a bunch of different values to see what works.
Yeah.
But the approach that I just laid out is actually a fairly principled approach. You want, on principle, the likelihood ratio to be increasing if the score increases. So that is just one way of doing this. There may be other ways. As I said, free parameters are always a little bit scary. They're always open to debate. So I'm pretty sure that there may be many other people.
Because it's the defense. Because I'm not sure if you're working with the defense or a prosecutor or whatever, but I can imagine that they are going to tweak the parameters, or they can tweak the parameters
Yes.
in their advantage as well, of course.
Yes, well, they might.
Okay.
They might. I think it's difficult though if you have an observation that is all the way here to tweak the kernel in a way that makes it positive for the suspect.
It's an interesting concept, yeah.
Yes.
To tweak it in a way that
There's actually a way to do this without smoothing, which is, I believe, the next thing that I will talk about. Unless there are any more questions now. There's also opportunity for questions later. Oh yes.
Yes, I believe you guys already thought about this, but let's say that one of the criminals just gives the phone to a friend on purpose.
Ah, yes.
Because that person, can you use it? Have you guys already had an idea of how can you maybe predict if the phone was used by the same person that normally uses it?
Yes, that sounds like a really interesting problem. It also sounds like an entirely different problem. That would be more like identifying a user rather than matching users. Just one of the assumptions that we have to make is that a person uses his or her own phone. If that assumption doesn't hold, then you cannot really use this method. Identifying who's using a phone based on other methods, I think it's a very interesting problem. Also a difficult problem. But that's not something that we're dealing with right now. No. Okay. So I think I'll just continue, and then if there are any more questions, we can get them at the end. So one idea, if you don't like the idea of estimating distributions and using a smoothing kernel, is to use the model outputs directly as probability estimates. So a logistic regression always outputs a score between 0 and 1. So let's say that it outputs 0.9. You may say, okay, the probability of getting these data under the prosecutor's hypothesis is 0.9, which means that the probability under the defense hypothesis is 0.1. So we divide 0.9 by 0.1, and we get a likelihood ratio of 9. So there's an alternative method of doing this. You bypass the entire what we call calibration on validation data. Currently, we are not researching this too deeply. There are a few theoretical problems with this. For example, I think it's difficult to make a strong theoretical argument that the output of a machine learning algorithm can always be reliably interpreted as a probability. We treat outputs more as scores than probabilities. One reason for our concern is that algorithms tend to make assumptions about the data. For example, a mixture of Gaussians may make assumptions that the data are Gaussian. What if your data are not Gaussian but exponential? Are those probabilities still reliable, or should we treat them more as scores than probabilities? So that's one problem with this method. Another concern would be what would you use as a prior? So if you have imbalanced data, your algorithm may learn that, let's say we have 10 times as many different user phones as same user phones. Your algorithm may just learn a very strong prior that phones tend to be different user. We're not sure if you actually want to use that prior. Actually, within the likelihood ratio framework, we're trying to avoid the prior and just focus on the probability of the evidence. You may set the prior to 0.5 artificially. It's often possible to weigh observations in your machine learning algorithms, but that's another thing that you need to do. And why set it to 0.5? Why not 0.4? It also opens up a lot of discussion. One other advantage of our current approach is that our method makes for more conservative likelihood ratio estimates. And I'll demonstrate that in the next slide. Welcome to the most difficult slide of the presentation. What we see here are some experimental results. The rows on this slide are different machine learning algorithms. The columns are, the two columns on the left are artificial training data that we sampled, that we generated. So these are the training data, and these are the validation data, and they were both sampled from Gaussian distributions. And they're also labeled data, because we know which data point was sampled from which distribution.
But this is phone data.
I'm sorry?
This is telephone data.
No, these are entirely artificial data. These are just to illustrate a principle. So these data are just two Gaussians. And if you have data from two Gaussians, you can calculate some actual likelihood ratios, because you know the probability of generating a certain data point from one Gaussian, and you also know the probability of generating it from the other Gaussians, because you know the parameters of those Gaussians. So if you have data that you generate yourself, you can calculate true likelihood ratios, which is what we did here. This column isn't too important. It's the result of predicting on the training data, but these columns are more important. This column represents on the x-axis the true likelihood ratio as estimated, or actually as determined from the parameters of the Gaussian. And on the y-axis, the likelihood ratio that is the output of our likelihood ratio system. So if you train a logistic regression classifier to classify these data, the probabilities match up, they actually match up really well with the actual likelihood ratios. So in the perfect case, you would just get a straight line. If the real likelihood ratio goes up, the estimated likelihood ratio should go up by the same amount. So these data are really nice. Of course, they are just Gaussians. And this column represents the method of using model outputs directly. And this method represents the column of the method that we just discussed, which is the method of applying a machine learning model to estimate distributions, apply the smoothing, and then calculate the likelihood ratios. So one thing you see is that after a certain point, our method becomes a lot more conservative. The likelihood ratios are actually on a log scale, and you see that you probably can't read it from here, but these likelihood ratios are just much higher than these, and after a certain point, the likelihood ratios, they sort of stop going up, which is nice because the worst thing that you can do with a likelihood ratio is to make a really large mistake, a really large likelihood ratio in the wrong direction, and a more conservative method runs a much smaller risk of doing that. There are also some differences between the classifiers. Most of them work pretty well. Logistic regression is nice. Naive Bayes works nicely. Decision trees, they give this very funny pattern. But the most important points are to be made by looking at the differences between the columns here. You may also be interested in measuring the cost of a likelihood ratio. So let's assume that you have a likelihood ratio system and you're tuning it. You'd like to ideally express its quality in a single number. There's a fairly common method for this. It's called the log likelihood ratio cost. And what this method does is it basically punishes large mistakes. So it considers the prosecutors and the defense hypotheses separately. And under the prosecutor's hypothesis, you would expect a really large likelihood ratio. So the smaller the likelihood ratio, the higher the cost. And for the defense hypothesis, it's the other way around. So if two samples are same origin, two phones have the same user, you output a really small likelihood ratio, the cost goes up. You output a large one, the cost goes down. And for different origin, it's just the other way around. And for every 2 orders of magnitude of a mistake that you make, the likelihood ratio actually, the cost actually doubles or halves. So this is a fairly common equation that you can use and that you should ideally try to minimize. There are also more sophisticated methods. You may say, for example, that morally it's a lot worse to convict an innocent person than to let a criminal go free. So you may tweak with these parameters and say, well, I think it's 10 times worse to convict an innocent person than to let a guilty person go free. And you can create your own evaluation metrics for your likelihood ratio system. Another common question that we struggle with is how much data do you actually need? It's really difficult to find an easy answer here. One obvious observation is that you need enough data to make a good estimate of your distribution. How much data you need for that, that's really up to your own expertise. And another very useful rule of thumb is that likelihood ratio should be more conservative when you have less data. So there's a common rule of thumb from the literature, from Vergeer, I think he's Dutch, 2016, and he basically says that likelihood ratio should never be larger than the size of the training data under the defense hypothesis, and never be smaller than one divided by the training data under the prosecutor's hypothesis. So if you, let's say in an extreme case, you only have 5 observations for each hypothesis, your likelihood ratio cannot be bigger than 5, and it also cannot be smaller than 0.2. That would be asking too much of the data. In this article, he actually goes on to lay out a much more sophisticated defense of this rule of this intuition. And it also involves the relative utilities of convicting innocent people and letting guilty people go free. Okay, so now a fun part. We're going to talk about how to use likelihood ratios and also how not to use them. What a likelihood ratio really does is it quantifies the relative probabilities of a certain piece of evidence under competing hypotheses. So that's all that it does. And as you may remember from the slide that laid out the entire equation, that's actually not enough to judge or to determine the probability of the hypothesis. It only gives you the probability of the data given the hypothesis. And that's a very different thing, and it's easy to confuse them, especially if you're not a statistician. What when multiple pieces of evidence are available, so let's say in a criminal case there may be evidence from cell phones, there may be DNA evidence, there may be other evidence, license plate, camera evidence. When these sources of evidence are entirely arrived at independently, you may multiply the likelihood ratios to get a much stronger likelihood ratio or a much smaller one. When different pieces of evidence are not arrived at independently, you should not multiply them for obvious statistical reasons. And the Netherlands Forensic Institute does not really say anything about hypotheses either being true or false. The only thing that we say something about is how likely data are given a hypothesis. Because saying something about the actual hypothesis would require both knowledge of all the evidence. You need to collect every last piece of evidence that is available to calculate all those likelihood ratios to make that judgment, and you would also need to know something about the prior probability, which is not our area of expertise. One way to not use a likelihood ratio is to commit the prosecutor's fallacy. The prosecutor's fallacy is encountered very often, especially in newspapers. Journalists often commit the prosecutor's fallacy. So for example, suppose that a fingerprint is found on a crime scene and it matches a person in a large fingerprint database. And the probability of a random match is 1 in 10,000. So these data are very unlikely. A prosecutor may say, well, the likelihood of the evidence is 1 in 10,000 for an innocent person. So the probability of this person being innocent is 1 in 10,000. And that seems to make some sense on the surface, but when you probe a little deeper, it's actually not a good application of the likelihood ratio. The prosecutor in this case forgets all about prior odds. Most people in the world aren't murderers. The prior odds of being a murderer is very low. So even if you match some profile with a low probability, that doesn't mean that you can use that probability and say, oh well, that's the probability of you being innocent. It also forgets about other pieces of evidence. Maybe perhaps the person whose fingerprint is matched has an alibi. That's also evidence. Perhaps his car was seen by a license plate camera. That's also evidence. And you cannot just take the likelihood ratio and treat it as a judgment of the probability of the hypothesis. That just doesn't work. There's also a reverse version of this. It's called the defense attorney's fallacy. It's also commonly made. Suppose that a fingerprint is found on a crime scene and it matches a person in a very large database. The probability of a random match is only 1 in 10,000, but there are 1 million people in the database. Now, the defense attorney may say, well, there are 1 million people in the database, so based on probability alone, you would expect 100 random matches. So the probability of my client being guilty is 1 in 100. That also doesn't make a lot of sense. It could be sort of true if there's no other evidence whatsoever, and you're also certain that the perpetrator is somewhere in the database. That's usually not the case. And one way to see it is that the fingerprint match narrows down the search for your suspect by a factor of 10,000. And in spite of narrowing down the search by a factor of 10,000, it still doesn't exclude the suspect. So you could say that there's now 10,000 times more probability mass placed on the suspect than there was before the fingerprint match. So that would be a slightly more reasonable way of looking at this. And I'll be happy to take additional questions. Yes. That's a dangerous statistical minefield that you're describing there.
Repeat the question.
Yes, sorry. The question is, how do you take into account the way in which you arrived at your evidence? So, for example, let's say that the suspect's phone and the prepaid phone are always close together. Well, how did we get our suspect? Did we get our suspect by taking a huge database of all the people in the Netherlands and singling out the person whose phone matches the prepaid phone the most? If that is how you arrive at your suspect, then it is almost self-evident that the likelihood ratio would be high, but that is not a sound application of statistics. So that's a very good question, and that is something that forensic scientists should always be very concerned about. Yes. Any more questions? Yes.
I'm interested in your priors, and in two ways. Actually, there is a prior on what data you can expect, and that was on your slide in the formula. But there is also a prior on the judgment of the error of a judge. And that's a prior about how many criminals he or she wants to go free. And that's another problem. And those should not be confused, because one has to do with the data sampling, and the other has to do with the legal morality.
Yes.
Those should not be confused, and I would like to hear your comments on those, on both, in fact.
Right. So, is your question that a judge may use his or her own prior probability of innocence?
I think they do.
Yes. Right. Well, the job of our forensic institute is really not to say anything about priors. So we basically just look at the evidence and determine its probability under hypotheses. And then the question that you raise is a very valid one, but I think it's a question that you should ask a judge. How do you deal with the presumption of innocence?
But they have not the foggiest idea about numbers, and you do.
Right. Yes, well, that's a problem, yes.
So, please comment on it.
Right, so I'm not really sure what to say here. So my instinct would be to just deliver the likelihood ratios and to not step outside my field of expertise and to not try to do the judge's work. So the judge may figure out how he handles his presumption of innocence himself, I guess. Yes.
How are judges educated in using statistics? Because most of the results you can get with statistics are counterintuitive, right?
Yes.
Just think of the Monty Hall problem.
Yes.
Which is Lucia de Berg.
Yes.
Lucia de Berg is another example. But so I'm just interested in, because this is very sound and we try to explain how it works. But do other people get it?
Right. Well, this is a problem for all forensic science, actually. I think judges cannot be expected to both know a lot about the law and also about telephones and also about statistics and also about fingerprinting. Well, perhaps a little bit about statistics. I believe that there are Bayesian statistics courses for judges and legal people. Is that funny? I believe that they, I think I've heard of those courses. I think it's a good idea to educate judges in the field of statistics. What they're doing is basically statistics. So I think it's really important. If judges don't properly understand statistics, things can go horribly wrong. The same can be said for experts. One remedy to the potential problem of just barraging a judge with statistics to the point where he doesn't know or she doesn't know what to think anymore is counter expertise. So when a complicated method like this will be used and explained in a court case, I think the probability is very high that the defense would get their own expert to give some to push back a little on our conclusions.
And
yes.
their own tweaking.
Do their own tweaking, and then it's up to the judge to figure out which expert is making the most sense, which is a really difficult problem, because in order to determine which expert is making a lot of sense, you need to be an expert yourself, which you're not. So yes, I think it's an unsolved problem. Yes. Thank you.
This is one possible solution for the problem. Have you all also explored other possible solutions?
Well, this is one that we're working on really hard right now. Another solution, I briefly talked about just using your model outputs directly as probability estimates. That will be a potential solution. Another solution is to not use machine learning at all. So for example, if you have two cell phones and one is in Den Haag and one is in Maastricht 10 minutes later, you can just say, well, these data are impossible under this hypothesis. It just cannot be that these phones are being used by the same person. So what we're going to do is we're going to see, let's say we have a database of 10,000 phone pairs. How many of these phone pairs can we just exclude really hard based on really ridiculous data that are just impossible? And then you can calculate a likelihood ratio based on that. It's a really crude approach. It's also a lot simpler. So perhaps that could be an alternative, but we're not really, we really like sophisticated approaches. Yes.
You talked about the course, your work is valid under certain assumptions.
Yes.
You also say, as long as you make those assumptions explicit, and a judge can
Yes.
can judge them. When we do our data science in business, there are always business experts who can make an informed judgment about assumptions that we make. But in this case, how would judges be able to assess the assumptions that you list, and how do you determine how many assumptions or what assumptions you can make so that it is still judgeable, if you see what I mean?
Yes, yes. It's almost the same problem as the problem of judges not knowing too much about statistics. If judges don't know too much about statistics, or if they don't know too much about the scientific field, how can they judge whether or not these assumptions are reasonable? Yeah, it's a difficult question. What we typically do is we make our assumptions explicit, and let's say that we're working for a public prosecutor. A case may come to us and we say, well, we can look at this problem, but we can only really say anything about it if we are allowed to make these assumptions. Do you think our work is still valuable if we have to make all of these assumptions? And then the prosecutor may say, well, I think those assumptions are reasonable, so just give me the research. If he doesn't think so, then there's just no point in doing the research. If there's no way to assume that people are not sharing phones, for example, then there's just no way to do the research. So I think it's mostly the prosecutor who will make that call, and then the judge needs to assess whether or not he or she agrees with the prosecutor. Yes. Yes?
Do you always work for the prosecutor, or do you also work for the defendant?
I'm not really sure. I can imagine that we would work for the defense. So this is more like a business question about how does the Forensic Institute work. Maybe you know, my coworkers in the audience. Do we sometimes work for the defense?
Yeah.
Ah, yes.
So you're also hired by lawyers for the defense?
Yeah, sort of.
Sort of, okay.
So then the defense says, yeah, we want to have somebody look at this, if it's true, and then the judge says, let the NFV look at it.
All right.
All right. So the answer is yes. It sometimes happens. I couldn't think of a case immediately, but it does happen. Yes. Yes.
Can you talk a little bit about the method again, about how you're actually extracting the scores under the two different hypotheses?
Yes. So which part of the method?
How you generate this data from the actual list of
All right. Yes. Yes. This is a tricky part.
my question is mainly, it sounded to me like each, and maybe I misunderstood, but it sounded like each change between the two phones
Yes.
was an instance, and sounded like
Yes.
independent. And I'm wondering, does that have any impact on the probability? Because if they are the same, then all of the instances are not independent.
Right. So there are always two phones, and if you observe one phone 10 times in a row, by definition the data are going to make sense locally within the phone. But the only thing that we're really interested in is how do these phones match together, and the records in our data that provide the most information is where you go from one phone to the other. So we just keep these transitions, and because it's possible to get a really high score on a feature, or really high speed, or really big distance between phones, but that's just not possible within a phone if the data are correct. So those data just aren't informative to us. Does it answer your question?
What is a unit that ends up on the probability chart?
Yes. So that's a tricky part. So there are two machine learning models. The first machine learning models just takes many of these observations. So each of these observations will receive a label as coming from a same user phone pair or a different user phone pair. So let's say that we have 100 phone pairs with 100 observations. That will be 10,000 records in our data set. So the first classifier takes all those 10,000 records and is trained on that. Then what we are really interested in the fictional crime case is not any individual record, it's the total pattern of how two phones are moving together. So what we do, let's say we have phone A and phone B, we add all these scores to bins, and we create 10 new features. So we look at the phone pair, what percentage of their individual observations were between 0 and 0.1, what percentage were between 0.1 and 0.2. We create 10 bins, and then those 10 bins are 10 features for a second machine learning model. So it's actually one alternative way to do this is to not aggregate the machine learning scores, but to aggregate the features directly. So instead of classifying each observation and then binning the results, you may also just bin the speeds. So let's look at all the speeds between the phones and create 10 bins for those. Then look at all the distances between the phones, take the average or take the min or the max or create more bins. So you can really make as many features as you like. But this is one that ended up working well in practice. Yes. So I hope that's clear now. Yes? Yes?
For your pattern, how big of a time window are you looking at? Or is it just X number of observations?
Yes, well, that depends on the case. So if a crime was committed and the prepaid phone that can be linked to the crime was used for, let's say, 4 months, then it would be reasonable to take 4-month periods. If it was only used for a few hours, it would also be reasonable to take from your collected data 4-hour periods, so that the data are as representative as possible for the actual case. So, and representativeness of the data is one of the most important things here. Any more?
This is not about the case, but you mentioned earlier that you work with different types of data, and I'm very curious. Could you just name some of the most unusual data sources that you have used for cases?
Unusual. I actually cannot talk about specific cases. I'm just not allowed to do that, but I can give you examples of the sorts of data. So the source of data that we work with are text messages from phones, perhaps entire server parks are seized by the police. We may have millions and millions of email messages. The financial administration of a company, emails within a company, like the Enron case. There were hundreds of thousands or millions of emails. Only a very small fraction of them were actually discussing the fraud that was going on. And no one has time to read a million emails. So one assignment for us could be to cluster those emails based on topic. We use license plate cameras, information from telephone companies, laptops, hard drives, tablets, basically anything digital that we can get our hands on. We're able to work with it, yes. Yes. Well, yes, we are very interested in the fit and the accuracy of our classifiers. But it's not the scariest thing in the world if your classifier isn't doing a really good job, because if it would classify at random, let's say it's a totally rubbish classifier and it classifies at random, well, what would your distributions look like if your classifier is just spitting out random numbers? Well, the distributions would basically be the same. So your likelihood ratio would always be 1. Which is a pity because you would like a higher likelihood ratio, but you're not in danger of making a huge mistake. So if you have a subpar classifier and that's just making random errors, it should, in this method, it should have the effect of making your likelihood ratio so conservative that you're basically not able to use them anymore. So there is a little bit of a safeguard against bad classifiers in our method. Yes. Yes.
One other question. You talk mostly of criminal cases.
Yes.
But what if the case is not criminal per se, but legal case? Because you have more legal fields that can use machine learning
Yes.
for detect bullying or maybe stalking.
Oh, yes.
Maybe criminal, but
Yes. Well, I can really imagine us doing work of that sort as well. Work not necessarily for criminal cases, but just helping other government agencies with their data. We actually do that a lot. But we wouldn't really use the likelihood ratio framework. The likelihood ratio framework is really a forensic science thing that is used in courts. If we're just doing a big clustering or a big search or making some nice visualizations or using machine learning in another way, we would probably find another way to present the data to our clients.
But what I mean is that for some cases you need the lawyers because you want to have a case. And so I'm not asking about visualizations you can do yourself, but you sometimes need the legal ground for it.
Right. So the question is, can we help people preparing a legal case?
Can lawyers say, okay, where do I have to go to do this kind of work and take it into court? Because not all evidence or work is admissible in court.
Right. So basically, if a lawyer needs help sorting through huge amounts of data, would that be something that we could help with?
Yeah, because is it the judge that can say, okay, now we ask an expert, or can lawyers do the same? Because
Yes, I believe lawyers can do the same thing.
resources are distributed in the legal system.
Yes. So you're afraid perhaps the defendants have a lot less resources at their disposal to do these complicated calculations. Yes. Lawyers can they can hire their own experts or appoint their own experts. They will be counter experts, and that's actually something that happens fairly frequently. And as we just heard, they can also sometimes contact the Netherlands Forensic Institute, yes, for a second opinion. Yes.
In line with
Okay.
this question, do you make all your results then available to both parties, including your algorithms?
Including the algorithm, I believe so. Yes, I think it's actually required that that the defense has access to all the data. I'm no legal expert, more of a, but I think
Matter of transparency, that's
yes,
actually the case.
I think that is typically the case. It will be very weird for us to, yeah, it will be strange for us to write a report and say, oh well, our results are very interesting. Yeah, you should have a look at them, but we're not going to show them to you. Just you're just guilty. No. That's not how it works, fortunately. No. No. Yes?
Your outcomes can have a potentially very big impact, of course, in people's lives. Can you
Yes.
shortly describe something like your quality assurance process?
Oh,
What
yes.
process do you go through?
Lots,
so
yes.
You can make a mistake without ever noticing.
Yes, there's lots of quality control. So for one thing, you have to write computer code to make these kinds of calculations. You never write computer code on your own. There's always another expert who reviews your code. And then even when your code has been reviewed, when a project is nearing completion, we appoint a separate expert at the Netherlands Forensic Institute who wasn't involved in the original project, and he basically repeats the entire project and sees if he or she arrives at the same conclusions independently. So there's a lot of quality control here because quality is really important. So yeah, it would be painful if a huge computer bug sends someone to prison. Or yes, yes. We go to great lengths to avoid that. Yes. Okay, I think those are the questions.
Make one last.
Oh yes,
I'm
sure.
sorry, I make too many.
I have all night.
Is there anything of this published? Do you
Not yet.
publication?
That's a great question.
People can
Yes,
refer to your
thank you.
methods and to your ideas?
Yes, so we are actually in the middle of publishing a scientific paper on this exact topic. I'll resume work on it within a few weeks with a lot of my co-workers. So you should see this in perhaps a year. Well, it takes a long time actually to publish anything. Perhaps a year and a half. I expect this to be a published method. Sometimes actually when we publish methods, they stop working because everyone will know about them, which can be a risk. Yes, there are also advantages to publishing your methods. If a method is peer-reviewed by many scientists, it's a great validation and also make the job of the judge easier. So we are just discussing what if a judge isn't a statistic expert. Well, if there are 10 papers, peer-reviewed papers that all use the same method, that are all supportive of it, that would be one data source for a judge to make his or her decision. Yes. Okay. Thank you.